Okay, so I start by trying to convince you that buildings and heating factors are really important for the energy transition. Then I speak a bit about the role of data for the energy transition and give sort of one example on more like the system level, so looking at information on the whole building stock, which is important, let's say, for the planning of policies or of measures in the context of the transformation, and then on data on the individual building level, so rather on monitoring and optimization of building operation. Okay, so why is heating and cooling important? So one reason is that it's about, so heating and cooling accounts for about half of EU energy consumption. Similar value holds in Germany, so it's really a very important share of energy consumption in that sector, and so it's really important to look into that. Another reason is that about 2/3 of the total EU gas imports go into the heating and cooling sector, so it's also very important in terms of energy security, and it's a sector where the share of fossil fuels is very high, about almost, so it's only about 1/4 of energy consumption that comes from renewable energies in the heating sector. So it's one of the sectors that have very high share of fossil fuels and where there's a lot to do for moving the sector towards climate neutrality. This is particularly the case in Germany. So here we can see the distribution of energy carriers in the heating, in the space heating sector in the different EU member states. Everything that is gray or blue are fossil fuels. And we can see that Germany is sort of in the upper level with having a very high share of fossil fuels. So it's a sector where there is really a lot to do. Also, it's a sector where we have very long lifetimes, so it's difficult to move ahead. And this even more puts a lot of pressure on the sector. And this is also why it is right now in the focus in terms of policy making. So now quite a lot of effort goes into the building sector. Another reason is in terms of greenhouse gas emissions. So in Germany, we have the Climate Change Act that sets legally binding targets for reducing greenhouse gas emissions. It sets these targets for each individual sector. And the building sector is the only sector of all in Germany that has always failed to meet the targets. So there were opportunities in the year 2020 until 2025, and the building sector is the only one that never has met its target. So again, this adds up to the list of reasons why the building sector is very important to deal with. And then when looking at the building sector in the context of the energy system, buildings are also increasingly becoming important in the context of the electricity sector through sector coupling. So using heat pumps, PV systems, batteries, and so on has sort of a direct connection then to the electricity sector. And so knowing and being able sort of to automate processes in the building sector is also very important in terms of grid stability and keeping peak loads at a level that is reasonable for the grid, for renewable energy integration, and also for flexibility. So in principle, the building sector has a large potential also to provide flexibility, but this depends on the way in which it is operated. And so there are some challenges with this. And one big challenge is the data on buildings at a system level. Okay, so in order to make plans on how to move forward in the building sector, it is important to have data to know about the energy consumption of these buildings. And we do have good data on some structural facts of the building sector. So we know the number, the type of buildings, so if they are single-family homes, multi-family homes. We have information on the construction years. We have information on the main energy carriers that are used. So this information comes from the census. So for a residential building, there is quite a lot of information, but what we don't have is good data on energy efficiency levels and on energy consumption in the building sector. Okay, so there is really a big gap of data in these two areas. And let's say the main tool to get information on this, which is implemented at the EU level, so all EU member states have these energy performance certificates. So this is sort of the key tool to provide information on the energy performance of buildings, okay? And so probably most of you sort of know the EPCs. In case you have ever rented or owned a building, you should probably know them. So these are developed or issued by qualified auditors and are supposed to provide information about the buildings. And so basically, this is a tool for the individual level, so that one knows about the energy performance of an individual building. But at the same time, this is also the only official source of information that gives an overall picture of the energy consumption of all buildings. Okay, so there is a database which includes not all, but a large selection of these energy performance certificates. And that is sort of the only official source of information how the building stock in Germany is distributed over energy efficiency levels. And there are two types of these building certificates. One is demand-based. So here it's based on calculations. So a person goes into the building, a person checks the isolation, the windows, and so on. And then does a calculation following a certain procedure in order to calculate the theoretical energy consumption of that building. Okay. And the other way of doing this is a consumption-based certificate. So this is based on the energy consumption, the real measured energy consumption of the past 3 years before issuing the certificate. And so it reflects real user behavior and is of course much easier because you basically just need the data, the consumption data. Okay, and this is both legally permitted to have these two types. Okay, and the demand-based certificates are mandatory for some older buildings. Okay, and now we come to the problem with this. So here we can see the distribution of energy efficiency classes in Germany based on the database of these energy performance certificates. And here we can see on the left-hand side the ones for single and two-family homes, on the right-hand side for multi-family homes. And on each of these graphs, we have on the left-hand side the demand-based certificates, on the right-hand side the consumption-based certificates. And there one can see at the left side that they look very different. Okay, so they look completely different. So one can see immediately that the calculations don't have anything to do with the consumption-based approach. Okay, and so as I said, it is the only official source of information that we have on the energy performance of our building stock. And we have the situation where these two certificates differ very considerably. Okay, and
can you give intuition why this is the case? So why is it so dramatically different?
Yes, we come to that. Yeah. So it's important to understand sort of what are the issues. I will come to some issues with the consumption-based, to some issues with the calculation-based one. Okay. Okay. So there are some proposed solutions on how to address this. I mean, there are some issues in the calculation which are clearly not reflecting the real behavior. So for example, there are some certain temperature levels that are set for the calculation. So saying in a normal room, you have 20 degrees, and then in real life, people don't have 20 degrees everywhere in the home. So these are sort of standards that are set in the norms that define the calculation that are just not reflecting reality. And so there are different approaches on how to address this. So on the left-hand side, we can see a picture where the people that did this analysis just sort of compared for buildings where they did have actual consumption data and they did have the calculated values. They compared this for quite a large number of buildings. And so on the x-axis, we can see the calculated energy demand, and on the y-axis, the actual consumption. And so one can basically see that especially for buildings with a higher energy consumption, the demand very much overestimates the consumption. So there we have this big difference, and this could actually also be seen here. So especially on this side of very bad buildings, very inefficient buildings, we have this demand calculation which overestimates consumption. Okay, and so what they did is to derive a factor. So for any energy consumption, for any calculated energy consumption, they derive a factor that is then applied to get consumption. Okay, and this is actually what is used in real life. Okay, so this is the approach that is used for evaluations of policy instruments, where they just use a factor that has been derived from a database where people have compared this. Okay, and so this factor is used to make up for the problem that the whole calculation is not at all based on real data and does not work at all. So it does not reflect consumption at all. And actually now, with the new buildings directives at EU level, which is in the process of being implemented, even more importance is being given to these demand-based calculations. Okay, and then the other approach that is sort of being investigated is to take a data-driven models. So what is done here is basically that one collects a lot of information about the building, so the information on windows, building ages, construction types, and then puts this into models that then try to assign a reasonable value for the calculated energy demand. Okay, so this is sort of not going into the building, looking at the window, but just taking some data. And so here, this is a graph from where people sort of tried different of these models. So looked at different models and estimated how well they actually reflect the consumption. And then they compare this to the normal approach that is taken now. Okay, so one can see that this is actually one that is the worst functioning one. So all the database models that they have tried out actually work better than what is applied right now in real life. Okay, so so we have the issue that the calculation-based model does not really reflect consumption. And now we come to the consumption-based one. Okay, so another approach could just be to say, okay, we give more importance to the consumption-based energy performance certificate. However, I will show you that there are also important issues with that. So one is, so it's based on the measured energy consumption of the previous 3 years. And then there are also some standardization processes that apply, where the measured consumption is then corrected for some factors, the most important one being a weather correction, because of course energy consumption in buildings depends very much on if it's a cold winter or warm winter. Okay, and then also for the location. So here the idea is to give an information on the energy performance of the building, and so there's a correction being done for the location of the building, reflecting the outdoor temperatures. And then it's also adjusted to a standardized building area, which is not the normal floor area. And now I would like to show you also a real life example of a consequence of not doing well the standardization in the consumption-based approach. And this is the example I would like to show you is in the context of the CO2 Cost Splitting Act. I will explain briefly what this is. Okay, so I will first explain what this law is, and then I explain what the issues with energy performance certificates have to do with that. So the CO2 cost pricing, cost splitting act, one important information that you need to know is that in Germany, we have a CO2 price applying to energy carriers for heating, so for oil and gas. This has been introduced, so last year was 2021, and it has sort of a price path going upwards. So every year this CO2 price increases. We are now in a corridor between 55 and 65 euros per ton of CO2, and then this will move into an EU system in 2028. So we will continue to have carbon pricing in buildings. And in Germany, we have a bit of a special situation that we have a very large rental sector. So more than half of the households in Germany live in rented dwellings, okay? This means that there we have the situation that there's a building owner that decides upon retrofit measures and that can, let's say, control CO2 emissions of the buildings. And then we have a tenant who pays the energy bill. And to account for this, Germany introduced an approach for splitting the CO2 costs between landlords and tenants. So if you're a landlord or a tenant, you may probably know that this is split. And this is done based on the energy performance of buildings. So in the individual building, if your individual building has a very low CO2 output, okay, low CO2 intensity per square meter, then the tenant pays all of the CO2 price. If the building is inefficient, thus having a very high CO2 intensity, the landlord pays the whole bill, okay? And now, considering the fact that I just explained that we don't have a good databases for knowing how efficient the buildings are, there was a bit of a situation when setting up this scale, because it has a total target that landlords in total over all buildings should pay about 50% of CO2 and tenants should pay about 50% of CO2. Okay, and so the question, where to put exactly the limits of the scale require information on the building stock. Okay, and so what one can do is to take different data, and the data source that was taken for this is the distribution of consumption-based energy performance certificates. Okay, so the one that we saw earlier, because here basically the consumption is what is important, and then census data, which helps to know how many buildings, what floor space we have and how they are heated, which is important to calculate the CO2 emissions. It depends because gas has a lower emission factor than oil, okay? So putting together these two data sources, one can model the distribution of the CO2 costs between landlords and tenants, okay? And the result of this is shown here. So these are these different classes from 1 to 10, the ones that we saw on the previous one. So in the left-hand side one, the tenants pay everything. In the right-hand side one, the landlords pay most of the CO2. And doing this exercise, one gets to the fact that landlords pay about 52%, and tenants 48%, sorry. Okay, so now, in the evaluation of this law, this was questioned, and there was real consumption data was used to check if this distribution is actually the targeted one of having 50-50 distributions. And so the data of measured consumption used here comes from billing companies. So in Germany, when doing the heating, the billing, the submetering, these are usually companies that do that for many buildings, and they have a lot of data on energy consumption of these buildings. And so these here in the three graphs, we can see the data from three different billing companies, where one can do exactly the same exercise of combining it with census data. And there already at first sight, one can see that many more buildings are actually in these classes where tenants pay a much higher share. And there are fewer buildings in the classes where the landlords pay the higher shares, okay? And so looking at the distribution from these data sets, one gets something between 26 and 36% of 10 for landlords and 64 to 74 for tenants. Okay, and so when we looked into that, we were first a bit surprised and didn't really know why we come to this large difference. And then one reason is the approach in which climate correction is done in the energy performance certificate. So how is this done? This is done using heating degree days, okay? So a degree day is defined as the difference between the indoor and outdoor temperature. So taking the average temperature of that day. And then these days are only counted if the temperature, the outside temperature is above a certain value. So in Germany, this is 15 degrees. So Germany, we are supposed to start heating buildings at 15 degrees outside temperature. Okay. And so the heating degree days are then basically the sum of this difference of temperature just on the days where that are counted. So where the temperature is below, in our case, 15 degrees. Okay. And so to normalize the measured energy consumption, what one does is to take the heating degrees days of a reference period and a reference location. Okay. So with that method, so this is the method how people adjust the measured consumption to location and time. Okay. And now the time correction is based on a very long time frame. Okay. And here we have a problem because the average temperature has increased very much in the previous years. So this is shown in this data, where one can see that in recent years, we have many more years where average temperature was higher than in previous years, okay? And so the problem is that when using a weather correction that takes a very long time reference period, this means that we correct and overestimate consumption basically for all years, okay? So these factors, so I put here the factors for the past 10 years, and we can see that in all years, I think it's just 1 year where the factor is 1, and in all other years, the factor is well below, well above 1. So this is always an upward correction. And this leads to the fact that the energy consumption in these energy performance certificates is overestimated systematically in all years, basically. Which leads really to a big distortion of the way in which, or the picture that we have of our building sector in Germany. And basically, so the way in which the statistical correction of the measured consumption is done, in the end leads to the fact that in 20 million dwellings, now the tenants have to pay more than what they were supposed to pay. So these are sort of simple examples where it would be helpful to really look into the way how energy consumption is corrected. Okay, so on the system level part, these energy performance certificates are the way of getting information on the building stock, but they have really important issues. And there is now a bit of a window of opportunity to look into that more closely, because there is the European Buildings Directive is currently being revised, and more importance is given to the energy performance certificates, and also more importance is given to databases with energy performance certificates as a basis to plan national measures. Okay, so these are increasingly becoming important, but they already are used all the time. So it's really a standard instrument in policy making and leading to the results as the example that I showed. So it's really important to have improved building data. And this is relevant for both of these approaches. So on the demand side, to adjust calculations to what is actually measured in real life, and on the consumption side, the question how to normalize the consumption. Okay, then we come to the buildings, the individual buildings part. Okay, so here, so now we go away from this overall building stock and move to the individual building. So here we have also a situation where many heating systems are operated really inefficiently. So with no control or poor control, outdated settings, and it's up to optimal operation. So I took here a picture from a project that I will come to in a moment, where together with the group or the sensors group at the Faculty for Electrical Engineering, we installed a system in schools. And what you can see here on the picture is the black line is the temperature in the rooms before we started the project. The red line is then after, where one can see that before going into these buildings, the temperature was always the same. So at nighttime, at weekends, it was always the same. So this is a very common situation, okay, that there is really no control at all, that the heating system just runs at full level all the time, okay? And that another situation is that no one ever looks at these data. So there is no data. So maybe they look at the consumption once a year, but there's not a lot of information and even less control on heating systems, okay? And so this is really a big opportunity that now there are many more, there's a large variety of technologies that can easily be installed in buildings and that can help to get more information and then also more possibilities to optimize or control. Okay, so the project that I just mentioned is this project called Suited, which is running at the Sensors Group, and where we installed in 3 schools close to Dortmund, we installed sensor nodes like the one that you can see on the upper picture, and then thermostats at the radiators in the rooms, okay? And so the sensors measure CO2, temperature, and humidity, and there are about 150 sensor nodes across the different classrooms in these schools. And they provide these data, I think, every half minute or something. So it's quite frequent data points. And then the thermostats control the room temperature via the opening of the radiator valve, okay? And this can be controlled then by the measured temperature. So the data that comes from the sensor node measuring the temperature can then be used to control the thermostat. And there are about 3,300 thermostats installed in the schools. So what is the aim? One aim is just to have a bit of a long-term monitoring of these parameters, okay, so to see how they behave. Then an analysis of the air exchange rates. So I come to that in a moment. The CO2 helps us to know the rate at which air exchange takes place, at least if there's no one in the room, there's sort of no new CO2 source, and then we just have it, okay? And that is used to identify weaknesses in the building envelope. I come to that in a moment. And then also to use the measured data to control room temperature and reduce energy use with that. And actually, so in this project, we actually take a very simple approach, really just taking the measured data to have a controlled temperature. And this already in last winter period led to energy savings of about 10%. So even with a simple approach, there is really a lot of room for energy savings. Okay, and regarding the airflow rates, so what we did is we wanted to know the air exchange rates of the rooms, because this is an important driver also for heat losses. So if there's a high air exchange rate, of course, a lot of heat goes out of the building. And so here we were interested. So we can see here a typical day at 8 in the morning, the kids come to school, CO2 values increase. One can see sometimes the window opening, and then after school, we have this decay part where there's now one in the room, okay? And basically this decay part is then used to calculate at an individual room level the decay rate of CO2 and with that the air exchange rate, okay? And we did that for all the different rooms in the school. Okay, so here every data point is one room, okay? Or every part on the x-axis is one room, and then we can see the different rates. And we can see here that there are some rooms that have much higher exchange rates. So these are the science rooms which have forced ventilation systems. Okay, so there it's not surprising that they have higher exchange rates. But then there are a few rooms that one can see here that also have higher exchange rates and that don't have forced ventilation. And then we look more closely into these rooms, and one could directly find the reason for the high exchange rate. So in one, this window doesn't really shut properly. In one, this is not really in the picture. So in the other one, they just sort of, there's a window that has been replaced with sort of a wooden piece. So it was very clear what are the inefficiencies in these products. And so this is an example where with really very simple measured data and a very simple approach to calculate the decay rate of CO2, one could directly detect inefficiencies in the building. Okay, so in principle, there are many possibilities to use sensor data to look at how the building performs. And so as a bit of an outlook, so here we looked at the decay rates, but this is basically only one part of how energy goes out of the system, or how heat escapes building. And there are, of course, many different heat flows. On the one hand, solar radiation going into the building, also heat gains and losses through ventilation. So this is something that one cannot really avoid. Also internal heat gains and so all different kinds of heat flows. Okay, and so in principle, it is also possible to use the measured data on temperatures. And so if it's spatially resolved data on temperatures and time resolved data on temperatures, plus the decay rates of CO2, one can learn a lot about the energy performance of the building, which can also help energy auditors that are actually issuing the energy performance certificate. So there's a lot of room for improving what we know about our buildings by using measured data.
Let me ask one thing.
Yeah.
So the sensors, is it more about you have some strategy when to turn on and off the heating, and the sensors are measuring the temperature in the room? Or is it that the sensors measure the temperature and then act upon this, like turn on and off the heating? Because, I mean, here you made the example that, okay, there's a problem with the room because the airflow exchange rate, or how you call it, is larger than there's a broke window or something. So is it like, I mean, taking the sensor data directly to change something, or is it to learn something afterwards?
Yeah, so for temperature, the sensor data is directly used. So temperature is measured, and this directly is used for opening or closing the valve. Okay, so basically increasing or decreasing the flow that goes into the radiator, which directly has an impact on the heat transfer into the room. Okay, and so for temperature, the data is directly connected and used. For CO2, it's not. So one could use CO2 data also for detecting open windows. It's more or less a classical application as well, because you can see if a window is open for a long time, and then you can either have an automated way of closing the window, or at least informing people. This is not done in our project, but this is an application that is possible and is being done. And then the fault detection, so what we saw in the windows in our case was just something that when looking at the data we noticed, but this is something that can of course be implemented also in building maintenance, but which is right now not really common, let's say, or it's not really done at all.
But the sensors only collect the temperature in the room, and then it gets getting too warm, then they shut the heating down, and then to keep the temperature at that level. But it does not include any weather data or weather forecast. Like in the day, it's very warm in the morning, and then it becomes cold over the afternoon, and you should increase then the heating. Which is not included.
Right now, we don't do that, but this is something that would be very useful. And also, so I showed you that the temperature is going down at nighttime. So there's a different reference temperature. And this, so the question, how much energy can be saved with this depends a lot on the building fabric. Okay, so in buildings that have a higher mass, it takes longer to heat up. And there it helps less to shut down or to turn down the heating at nighttime. And this can differ also between the rooms depending on the exact location, windows and so on. And so there is a lot of room for doing much more optimization. So learning how long it takes for the heating system to heat up, also scheduling. So right now we have just a timed schedule of saying, okay, at 3, there are no people at school, but it can of course happen that they have activities in the afternoon. And so this can be done on the one hand through manual scheduling or also connecting to CO2 measurements, which tell us if there are people in the room. But then again, this needs to be connected to this phase of heating up. So there is a lot of room. So this is the first project where we don't do all of this, but there is a lot of room of improving this control mechanism. So here, as I said, we saved about 10% of energy, but there is room for more when doing more advanced controlling. Yes.
Yeah, since you already mentioned the mass of the building or probably proper insulation will have a similar effect. So there is an energy consumption reduction, even though one has to probably reheat more than in the case when we just maintain a certain temperature. So we can save energy with this going up and down in the temperature compared to just maintaining a certain level.
Yeah, so in most cases you do save energy. So it's mostly the case in very late buildings, so that heat up very easily. There you have lots of energy savings. In very old buildings with, let's say, very big stone walls, it's less. But typically you save energy. There can be cases where you don't. In that case, you do.
Okay, and then the economist in me comes with the question, is it possible to, or how long does it take to break even on the thermostats? Because they are not cheap, at least for if you just buy a few. And is there an approximation for your example, for instance, that you have looked at, okay, we bought 300 of these thermostats. How long would it take to break even on the costs?
Yeah, so in our case, as this has been a research project, the colleagues from the census group actually fabricated these thermostats. And so they were really cheap, not counting the hours that they spent. And in the buildings where we worked, I would say the payback time of the commercial solution would be something like 3 to 5 years. So not a long time because they were running really inefficiently. There are studies where they looked into the use of thermostats in households, and there they got very mixed results because, of course, it depends a lot on what you did before with the heating system. So if you turn down the heating system every time you leave the home, then the thermostat won't really help you because you're already controlled. And so they asked people how often they touch the thermostat themselves, and this was between never and several times a day. And depending on that, the smart thermostat sometimes also caused an additional energy consumption. So the payback time depends a lot on how the system is operated without control. And in these public buildings like schools, it's very common that there is really no control at all, because also the people that pay the energy bill are typically not the same that are in control of the heating system. At home, it depends very much on how you operate the system.
Yeah, okay.
Yeah. And I mean, in this case, we really just control the thermostats. There is, of course, also room to do controlling directly in the heating at the boiler level or at the general entry of heat flow into the building, which at that case wasn't possible for some reason. Okay, so concluding on this second part, monitoring and optimization, there is an increasing use of sensor data and smart thermostats. Also, they are becoming cheaper and easier to install. So there is quite a lot of potential to use this in real world conditions. At the same time, this is really not used very much. So there is a lot of room for improvement on that, both on the diffusion side as well on the side on how these systems actually work. It's on the one hand for the control directly reducing energy demand, but also on the level of identification of inefficiencies, opportunities for optimization. So really also in the whole sector of energy audits, it would be very helpful to use sensor-based methods in order to be able for the auditor to find out more information about the building quickly and easily. So we showed in our project, but of course there are many other projects where these smart control strategies can contribute significantly to reducing energy demand. And so having this overall picture of the building sector very much based on fossil fuels, this is sort of an easy and fast way of getting at least some reductions. Yeah, this operational data really gives a lot of opportunities to work with on building level, on level of how people use the building, thermal behavior, air exchange rates, and so on. And so overall, I hope I could convince you that the building sector is really interesting and important sector to look into for many reasons. And that in that sector, we really have a nice and growing opportunity to make use of data to reduce energy demand, optimize operation, improve characterization, and get a better plan for retrofit strategies. So if I better know the inefficiencies, it's easier to plan. So better data and analytics can be a key enabler for the energy transition in the building sector.